I am going to be talking today about temporal exponential random graph models. So in contrast to the talk that Tom just gave, this is going to cover less material. I am not quite the engaging and concise presenter Tom is, so I cannot cover a whole book in 45 minutes, unfortunately. But what my hope is today that we're going to be able to take a deep dive into a temporal exponential random graph model, or a TERGM, talk about what it is, learn how to implement it, learn how to interpret it, learn how to figure out if it's any good, and then figure out how you might want to apply it in your own work. Now, you heard Jim use the word crime and methods a lot. What you did not hear him use talking about me is health, and that's because my background is not in health. And so what we're going to be doing today is talking or using an example data set, which is actually a conflict between nations and the evolution of alliances between nations over time. And the reason we're using this data set is partly because network panel data is hard to come by, and partly because it, in my opinion, shows the extreme generality of TERGM. That we can use it for a pretty widely defined type of node set, which distinguishes it from alternative network panel models like the Siena models you'll be learning about tomorrow, which are restrictive in some ways, but actually really liberating in others. And so we'll be talking about why that's the case. So before we jump into it all, I do want to warn you, one of the models here actually takes about 10 minutes to run. And that model is right down here. And so if you want to run, if you're following along today in the R script, I encourage you to actually start running everything through line 166 right now, so, which I've already done ahead of time, and that'll allow you to kind of keep up as we're going through. OK. So the fundamental idea behind TERGM is that what we're trying to do is create a model of network change. And we're trying to create a model of network change that captures interdependencies between data points. So my understanding is you all have talked a bit about ERGM today. And what the temporal exponential random graph model is trying to do is take the ERGM framework, specifically its generality, its ability to account for exogenous edge-level processes, node-level processes, dyadic processes, and endogenous statistics, and extend it to a longitudinal framework. So the fundamental question, stated in its most general form that TERGM is dealing with, is why do ties change? And so we can think about these tie changes as relating to a large type of relational phenomena. It could be, why are people getting married? What creates structures and kinship networks? Why do people become friends? What shapes social cohesion? Or what causes somebody to buy drugs on the darknet from a specific seller? These are all very general ways of talking about relational phenomena that we can treat as the dependent variable in TERGM. So what makes TERGM distinct from some other types of longitudinal network models is it's specifically concerned with network panel data. What we're assuming is that we have at least two measures of the same network at different points in time. We can allow for the node set to change, but we're assuming that the fundamental network we're trying to measure is not constant, but is the same phenomenon measured at distinct points. Now, there's some interesting features of network panel data that are important to get a handle on before we jump into applying a TERGM. The first is that there's an implied assumption here that tie changes are coarse. And what I mean by a coarse tie change, it means that the tie we're looking at, or the relationship, is assumed to be relatively stable. And so if we're talking about something like a friendship, I mean, we're not kind of like saying, I will be your friend between 1:15 today and 1:30 today, unless we're very strategic at conferences or something like that. Then that might actually work out. But in the most part, ties are assumed to be relatively stable and move when something moves upon them with kind of ambiguous timing of a tie forming and a tie dissolving. This makes it actually distinct from other types of longitudinal network data, such as relational event data, where timing information tends to be extremely well-defined and easily ordered. The second consequence of having a relatively coarse measure of tie change is that it means that when we have multiple measures of network data through panels, we don't know exactly when ties change. And so in this example here that's put up on the panel or on the screen, we can see that there has been some momentous change in the network. We went from, well, these are actually two different simulated networks, but if they are the same network, we went from something that was a small worldish structure with high levels of localized clustering and relatively low centralization to something that is relatively consolidated, follows kind of a chain link structure with preferential attachment to two highly connected nodes. So we know there's been a massive change in topology, essentially an elimination of clustering, higher amounts of connection to central nodes, but we don't know the order of those changes. And we don't know exactly how that change process unfolded in this unobserved moment in time. Now, this problem in itself isn't actually unique to network data. if we think about panel data in general, if we're measuring something like, are you a smoker? What this is implying is a sequence of kind of events in the past 6 months or something like that. How many cigarettes have you smoked? And now people are reporting information about whether that behavior has changed. So we still, in this instance, don't know when the smoking behavior changed. But what we're able to do is make some assumption that our unmeasured component is uncorrelated with the change process and whatever effects we're trying to identify. In the case of TERGM, we're actually going to be making that same type of assumption, and we'll talk about it a little later. But the assumption comes with additional caveats because everything we don't observe is actually interdependent, right? It's a network structure where some endogenous processes, such as when does a triad form, are actually contingent on other ties existing before that next tie. And we can't measure any of this directly. And so the way TERGM deals with this and the way stochastic actor-oriented models, which you'll learn about tomorrow, deal with this, are quite distinct and make them competing in terms of some of their assumptions and in terms of some of their modeling capabilities, but ultimately designed to handle with similar data structures. So we'll be focusing today on TERGM, and the heart of TERGM is an autoregressive framework. This approach is easy to implement and is actually a relatively small extension of cross-sectional ERGM. And so we'll start today by kind of doing a quick review of cross-sectional ERGM, hopefully trying to anchor it in a very familiar model, which is logistic regression, before introducing additional complexities, and then moving on to extensive cases. So we'll start with the most kind of earliest, simplest form of TERGM, and then we'll move to separable TERGM, and also kind of what I call between within TERGM, which allows you to account for stability and change at the same time. One of the benefits of TERGM that we'll talk about is the assumptions it makes tend to be relatively flexible in terms of it's not making explicit assumptions on what drives network change, in contrast to Siena models. But the trade-off of this is that in many cases it actually provides a less realistic representation of the unobserved change process. Now the trade-off here is it enables us to actually model some social or health contexts that we could not model with alternative panel data models. However, it also means that we have to be very careful about what exactly we're trying to specify and whether it's reasonably captured, because TERGM does not adjust for some of the things as its competitors. And if anybody needs a clarifying or a quick question point, just interrupt me. This is my second lecture today, so I might just be going ahead with it. OK, so we'll start with a quick review of the most general case of a binary exponential random graph model. We're assuming that we are observing some network out of a distribution of potential networks that could be observed for a fixed set of nodes. And what we're trying to figure out is what increases or decreases the probability of observing our network as opposed to all other networks that could be observed on a fixed set of nodes by perturbing the ties. So we have our binary realization of the potential network, which is just denoted by y. We also have our sufficient statistics in the network lingo, which are essentially counting how many triads or endogenous structures we observe on the network, and what is the sum over whatever exogenous attributes we might want to include, such as race, smoking behavior, gender, any other kind of node-level dyadic characteristics. Theta is our parameter vector. It's just telling us what increases or decreases the probability of observing our network. And this ugly Greek symbol eta is telling us that we can actually specify an arbitrary nonlinear functional form. And so this is the most general case of ERGM, which we refer to as a curved ERGM, which counts for nonlinearity in the structural component. This is not the most intuitive way to think about ERGM. This is the most complicated way to think about ERGM, and it's the way we typically talk about it in the literature because it has very desirable properties for estimation. The easiest way to think about ERGM is, found the markers, is as a logistic regression. And so in the simplest case of ERGM, what we can write, that one's dead. We can write the model as a logistic regression. That one's dead too. Let's see. There's a whole arsenal back here. You know, over at UNC, they're always like, Duke has money, but apparently not for Marcus.
We use our markers.
Oh, sweet flex. Thanks, Jim. So the simplest way, there we go. Now you have to deal with my handwriting. The simplest way to think about ERGM is simply as a logistic regression of the probability of observing some tie at a dyadic level. And so this functional form should look relatively familiar. Because what it is the exact functional form of logistic regression. What we have here is the probability of observing whether a tie exists or does not exist, divided by the probability does not exist. So this is just our log odds ratio. And over here we have our coefficients. We're using theta because we like to be fancy, but we can call them beta if it makes it feel more familiar. And then over here we have our change statistics, or our input variables, that are increasing or decreasing the probability of observing a tie. And so our data structure, if we arrange it to fit into this, go ahead.
Is that just a fancy way of saying covariates?
Yes.
Okay.
Yes. Covariates, if that works better. Absolutely. We like to be fancy over
I know.
here.
I was like, well, that was 7 words to say.
I know. Yeah, you get a lot of verbiage from me. I'm sorry about that. So what we're doing here essentially is what we're predicting is the probability of observing a tie given all dyads that we actually observe in the data. So say we have a simple triadic network that looks something like this. We have 3 nodes. Our data set is essentially going to be each pair of dyads arranged here with the ties we observe written in terms of 0s and 1s, and then any predictor variables we want to include over here on the right-hand side. So in this case, let's say these two are boys, this is a girl, and what we'll have here is some covariate for sex, and we'll count up how many boys are involved in the connection as opposed to girls. And this is in essence what we're going to estimate. Now, in this limiting case, what we're essentially saying is that the sex covariate, whether a node is a boy or a girl, is exogenous with respect to the tie. And so what this means is that actually, if we just took this very simple model, where we have one independent variable assumed to be exogenous, and a dependent variable that is a tie, we just fit a logistic regression, and we call it TERGM. And we can interpret the results as essentially saying the log odds of observing a tie increase by theta depending on whether a dyad includes one or more increasing number of boys as opposed to girls. So this is the simplest case, and the reason I like to emphasize the simplest case is because our fundamental interpretation of ERGM and TERGM results can still be brought back to this kind of logistic regression-esque type of model, even when we get to more sophisticated cases. But the difference is, as soon as we start including endogenous stuff, we actually can't simply estimate the model as a logistic regression. Once we include anything endogenous, now we have to use this model, this representation for estimation. And accordingly, if we try to fit a logistic regression, we get what we call pseudo-likelihood, meaning our estimates are biased. Specifically, our standard errors are worse biased than our estimates. I swear that's a phrase. Meaning that we tend to get relatively small to moderate bias in our coefficients and bad downward bias in our standard errors. So what does this actually look like? Well, if we are to include an endogenous component to this model, what we're essentially going to be doing is trying to situate the model in what I think of as a potential outcomes framework. And so rather than simply modeling the probability of a tie, whether it's a 1 or a 0, we are going to model the probability of a tie conditional on y minus yi of j. And what this minus sign is indicating is that the rest of the network is held constant when we calculate our endogenous statistics. So what this means is we can think of a focal tie. We'll start with a 1-2 tie. And what we want to figure out is, does this tie actually close a triad? Now, if we were to simply predict the presence or absence of a dependent variable conditional on whether a triad exists, we're going to get an endogeneity problem. We can't ever see a triad without a tie being there. And so instead, what we do is we model the change in the triad count as a function of the network that could exist if we were to change a focal edge. And so this is why we use this delta plus sign. It indicates the change. So what this means, say that we induce 2 potential outcome networks. One is the potential outcome when the 1-2 tie actually does exist. This is the network we observe. And what we want to figure out is how many triangles exist in this network. Now, for those in the back who might be like on their tippy toes by now, the answer is none. We don't see any triads. When we remove that tie, we also don't see any triads. So what we're going to do is subtract the difference to get our change statistics. And for this 1-2 tie, we're going to say the number of triads that are form when this tie is created, conditional on all else constant, is 0. We're going to do the same thing for the 1-3 tie, which gives us no unique triads. But now we're also going to do the same thing for the 2-3 tie, which for in the back currently does not exist. When we create that tie, holding the rest of the network constant, it actually creates one triad. And that's our predictor. And so if we get a coefficient for our triadic closure model, what we are essentially saying is if a focal tie closes a triad or increases the number of triads that would not otherwise exist, it is more likely to form. So I'll say that again because I'm getting some squints. If a tie closes a triad that otherwise would not exist, it is more likely to form. Why is that? That's if we get a positive coefficient. In this case, we might get a negative coefficient, in which case we could say if a tie closes a triad that otherwise would not exist, it's less likely to form. Why? Because we don't observe any triads in this network, right? So this is how ERGM deals with an endogeneity problem. And even though the complexity of this representation and the potential outcomes written here are a little fuzzy or kind of strange to think about, we're still essentially providing an interpretation in the form of a logistic regression-esque model. It's still an increase or decrease in the log odds. We can still exponentiate theta to get an odds ratio. We can still feed our predictions through a logistic link function to get predicted probabilities at the tie level. Or, if we want to be really fancy, we can actually do the macro interpretation too and talk about what networks are more likely to be observed, conditional on specific features. Okay? Mm-hmm.
So for the overall, like, you're saying the natural electric form, is that a rule that you impose, or that's a mismatch?
It's a rule I've imposed. So yeah, let me reiterate this. So if we're saying if the coefficient for theta is positive on a triadic closure, then we can say a tie that closes a triangle is more likely to form as compared to a tie that does not. If the coefficient is negative, as would probably be the case in this instance because we see no triads, then we can say that a tie that closes a triangle is less likely to form compared to a tie that does not. Mm-hmm. Do we need other clarification questions before we jump into the dynamic setting? Cool. All right. So ERGM adds a lot of complexity. It's a different way of kind of thinking about tie-generating processes. But one of the really desirable properties of ERGM is it allows for a lot or an extremely wide range of possible specifications. We can count for things endogenous to the network structure, as well as kind of the classic exogenous attributes like sex, race, smoking behavior, whatever, that we want to include to predict tie formation. When we get to the dynamic case of TERGM, what we're actually going to do is extend this basic framework for cross-sectional data to the longitudinal setting. By really, at its heart, we're just expanding our adjacency matrix. And so what we're doing here in the world of ERGM is we're arranging our data into an adjacency matrix with, if we have this limiting case of a triadic network, it's going to be a 3x3 adjacency matrix. And in a TERGM, what we're going to do is essentially expanding this to what's called a block adjacency matrix. So what we have here is rather than taking one simple network representation, which is the triadic network, and I actually did not plan this out, it's the same network as on the board, which is great, but it also shows I don't have many unique ideas. So we start with this representation, which in this example of a classical ERGM is a cross-sectional single measure of a single network. But now what we have is multiple measures. So now what we have is two time points of the same network where one new tie forms between the two observations. So our single adjacency matrix that was represented here now gets expanded to be a block adjacency matrix where we have multiple measurements of the same network at distinct moments in time. So rather than the dimensions of the matrix being n by n, or in this case 3 by 3 because we have 3 nodes, it becomes nt by nt, meaning we have distinct adjacency matrices for each time period and each set of nodes at that time period. And so we call it a block matrix because we get blocks. So we can break our block adjacency matrix into square components which represent the distinct network panels. So in this case, we have this diagonal entries representing the distinct network measurements. Here, the network before the tie changes. Here, the network after the tie changes. And then the off-diagonal elements are simply zeros. And the reason they're zeros is this is essentially a tie here would indicate I have a connection to somebody in the future. And so we're fixing these at zeros and only estimating the tie changes that we observe. So the basic idea behind TERGM is once we arrange the data into this format, we can actually fit an exponential family random graph model, some specification of ERGM, to this data structure, and then try to deal with whatever autocorrelation that comes up because of the sequential measurements of the same data. And one of the things that's really, really cool about TERGM is this, because the data structure is so flexible and the model is such a minor extension of traditional ERGM, is it actually allows us to fit generalized cases of ERGM to longitudinal data as well. And that means we can use TERGM for things like weighted networks. We can do TERGM for very long time periods as well. It's an extremely flexible specification. So one of the issue that we do get if we try to fit a TERGM to this exact specification is what we would have is essentially a dependent variable that looks like this. And what we would get is a model that is predicting every single tie we observe at any point in time. But usually what we're trying to deal with, though not always, and we'll talk about cases that don't make this restriction, is what we're usually trying to deal with is tie change. And so what we're going to do to handle the problem of autocorrelation, or essentially the persistence of some ties across time, is to simply control for a prior version of the network. And so what the TERGM does, at least the first version introduced by Haneke, Fu, and Xing, is we're simply controlling a lagged version of the network into the model as an independent variable. We're going to specify it with an offset parameter equal to 1. And what that offset parameter is doing is essentially holding constant all prior tie observations without actually predicting their effect. And so it's treating these as a nuisance or a noise parameter. As a consequence of this, when we're using TERGM, we usually, again, not always, means that we're using t-1 observations. And so what we're essentially doing is conditioning on the prior network to predict the now network. And that's providing one burn-in period. So even though ERGM is extremely complicated, when we get to TERGM, we're really just adding this one term. And that term is the past value of the network. So we still have this extremely general functional form, but now we're conditioning on our prior network observation. We're predicting the next observation as a function of now and anything that changes in between panels. So we have yt-1 on the right-hand side of the equation to account for autoregressive processes. We're treating it as an offset, so we're not actually trying to absorb the effect of that prior time panel, though we could if we actually wanted to, in the traditional model, but instead we're just trying to hold it constant. And we'll talk a little bit later about what that implies for the change process we're examining and why that's meaningful to think about in the case of TERGM. We can interpret theta similarly as before. Again, what I really want to emphasize is we're still working within a framework that is very similar to logistic regression. But now what we're talking about is the increase or the decrease in the log odds of a tie forming. And so if we, for example, were to model a TERGM with this type of functional form, and let's say we just have sex as the independent variable, a positive coefficient for sex would tell us that boys are more likely to form new ties between panels as compared to girls. A negative coefficient would mean boys are less likely to form new ties between panels as compared to girls. Or if we want to state it in terms of log odds, positive coefficient would mean boys have higher log odds of forming new ties between panels compared to girls. Negative coefficient, boys have lower log odds of forming ties between panels compared to girls. Again, we can exponentiate those coefficients for odd ratios, feed them through a logit link function to get predicted probabilities. It's all good. We're still working within a general logistic link function. Okay? Okay. Do we need clarification questions before we get into the first R component? Yep.
Understanding, like, if you were interested in, you might be like interested in the network at time 1 and do an ERGM, and then like do TERGMs from there to understand how things change. Is that just getting that conceptually right?
Sorry, you trailed off at the end there.
I getting that conceptually right? Like you would initially just do an ergom to understand like the base network maybe, and then the TERGMs would tell you just like change from that.
If you want to, yeah, so it depends. So if you're interested in both the base network or the stability and the change, you could treat it like that. We'll actually talk about cases of TERGM later if we have time that can model the change and the stability separately. And so you could actually do it in a more general case of TERGM, which we haven't gotten to yet, if you wanted to. But it could also be the case that your research question is fundamentally about change. And so one of the advantages of the network panel data is similar to panel data in general, which is that we're able to account for causal order if we want to, including like lag covariates, things like that. We're able to account for unobserved unit level heterogeneity if we want to stratify. Random effects are a little more complicated in the ergom framework, but if we want to stratify, we could do something like that. And so by going into the longitudinal framework, we get a lot of the same types of advantages we get with classic longitudinal data. But if we wanted to focus on what is the starting condition in addition to the change process, we're also able to do that. Yeah. Good question. Do we have other clarifying questions?
You just said you can also have random effects within there, and like, does that mean like nesting and things like that?
You can. You hear my pause, it resonates. It's because right now we have two frameworks for dealing with random effects in ergom and TERGM. One is a framework that only provides pseudo-likelihood, so we don't have exact likelihood estimates. Simulations suggest those standard errors and point estimates are a bit more conservative, and so some people like that, but we haven't derived maximum likelihood estimates for a frequentist TERGM. We can get random effects in a Bayesian framework if you want to estimate this as a Bayesian model, which is also possible. And so my big pause is because it's not that we can't do random effects, but the random effects we usually like, which are like restricted maximum likelihood, empirical Bayes kind of things, gives us p-values as frequentist mostly, we haven't got there yet with TERGM. Good question. Okay. So what we're going to do is we're going to switch over to R, and what we're going to start by doing is introducing a dyad-independent ergom, or TERGM. And a dyad-independent TERGM is a way of saying that our TERGM is going to be reducing to a logistic regression. We're going to estimate the model without any endogenous stuff, because endogeneity gets weird in TERGM. And we're going to interpret these results as reflective of some exogenous process. So we'll switch over to RStudio. And the three packages we'll be relying on today are StatNet, BT, ergom, and we'll do a little bit with ERG margins, but not a ton. So most of the estimation that we'll be talking about today and most of the TERGM utilities we'll be using are implemented in the StatNet framework. StatNet is extremely flexible and has done a lot of work on developing TERGM and ergom, but there's a specific estimation routine in BT ergom that can be very useful when you're dealing with large data because TERGM can get computationally intractable very, very quickly. So to start, what we're going to work with is the alliances data. So this data are loaded from the BT ergom package. And what the data represent is a list of networks where every node is a country, and each relationship is an alliance between those countries. And so the network is non-directed. We have 164 observations. We have 767 edges. And what we have here in terms of what the ally net is actually representing is a list of network objects. And so this goes back from the year 2000 to 1999 to 1998. I think it goes all the way back to 1980 or 1981. And so we have 20 observations of the same network here. Now, for simplifying purposes, what we're going to do is limit this just to the 1990 and 2000 network. And that's just because, again, the more panels we add to a TERGM, the more computationally intensive it gets. And we're trying to work with something that's a little more tractable. So usually in terms of data structure, when we're working with TERGM, we don't always have to, but it's often easiest to work with lists of network objects. And so all this code is doing is saying, take this first network object and the second network object and collate it together in a list that we can query with square brackets. So we can use the basic StatNet functionality to do some simple visualization with the gplot command. And so all this ally net square brackets 1 is saying is let's plot this very first observation of the network, which is what the International Alliance Network looked like in 1990. And so we can see some amount of clustering over here. There seems to be relative consolidation among what we might expect to be a few key factions. Maybe I'll blow this up a little bit. I have a bad habit of not zooming in on network plots. So we can see we have a ton of isolates around the perimeter. We have one kind of cohesive group over here. It looks like if we were to use like community detection lingo, we probably have about 4 or 5 major communities and then a ton of little isolates. Everybody's kind of connected over here through a couple of influential countries. We have one kind of brokering country here, relatively distinct factions here, and then a couple of alliances spanning. And we can do something similar for the second network, which is just the alliance network plotted 10 years later. And so all we're doing here is extracting the second network and plotting what it looks like. And what we can see is it actually looks like there's been kind of a shift in these little factions. So we had this kind of removed cohesive community that was off in the margins. Now it appears to either have totally splintered or been integrated into this main network component. Previously, we had about 4 communities in the main component. Now it looks like we're up to about 6 communities in the main component. And so we've seen some amount of integration happening. So we can start to think about several hypotheses about what's driving network change, or why do nations form new alliances with one another. And one argument could be it has something to do with polity or the level of democratization. So this polity measure is simply a measure of democratization that, don't quote me on exactly what it means, but the higher values mean more democratization, lower values mean more authoritarian tendencies. And we can measure it at both network panels, where we see kind of an upward or kind of a bimodal distribution with some strong state centralization, some high democratization, and then some folks in the middle. And at the second time period, or in the year 2000, we actually see a pretty strong lurch towards democratization in general, with a decrease in kind of the authoritarian side, a decrease in the middle people, and then a high level of democratization on the right-hand side. We can also think about alliances as being about capacities for defense. And so in this sense, the C-Inc measure is again capturing how capable a particular nation is at defending or sending troops if another nation were to be invaded. And so higher values we can imagine being especially influential alliances because people want to be protected, especially if they don't have standing militaries of their own. And we can again see that there's a somewhat shift in the distributional shape here. This one's a lot less dramatic, but there's a bit of a kind of a nudge away from a highly zero concentration in the prior panel. So in the language of TERGM, these are all exogenous attributes because they are not calculated on the network itself. What they are is provided as aspects of the nations, the level of democratization and the capacity for defense. And so now what we'll do is actually get into specification. So we can pull up the help page to get a sense of what the TERGM command is actually doing. And what we'll find is a lot of really extensive details about the potential estimation strategies and specifications we might want to use in order to fit a TERGM. In this case, what we're going to be doing is using the simplest instance of TERGM, which is one that reduces to a logistic regression, because we're only providing stuff that is assumed to be exogenous. Because TERGM is implemented literally using the underlying machinery of ERGM, we can actually find all the specification terms we might want to use in TERGM through the ERGM help pages. So TERGM doesn't actually have a separate suite of sufficient statistics or change statistics or endogenous covariates to include. What it instead has is an overlapping help page that aligns with the ERGM help pages we saw before. And so if you spend a lot of time in these help pages, like many of us I was going to say enthusiasts, but maybe nerds is a better word, then you can find that we actually have a ton of support for a wide range of potential sufficient statistics, change statistics, endogenous and exogenous processes we might want to include. The StatNet group has also recently implemented a lot of utilities to specify your own interactions and your own endogenous statistics. So if there isn't something provided here that you want to include, you can write it yourself, and include it that way. So we'll use this pretty simple specification of TERGM, and we're going to talk about a handful of key quirks for the specification. So the first is, rather than using the ERGM bracket, we're using the TERGM bracket. The second is that we are specifically modeling the dependent variable. Again, recall that the dependent variable is not necessarily a network in itself, but is a list of networks with 2 entries. And we're modeling it with a wrapper here that says form. And form is short for formation. What it means is that we are predicting why new ties are created. So this is the simplest case of TERGM. But what we're going to talk about shortly later is how we can also account for asymmetric processes, including tie dissolution and tie stability. So right now, we're only modeling why new ties form, and we're representing it as a function using the formation wrapper. everything we include in the formation wrapper are our covariates predicting why ties are more likely to change. So the edges term is acting as the intercept. This is the conditional baseline probability that a tie will change by random chance after we've included everything else. The node cov stands for node covariate. It works for undirected networks. And this is how we specify a continuous variable on the node level. So the node covariate for polity is telling us, is there an effect where alliances are more likely to be formed if it includes a node with higher, or a country with higher levels of democratization? The absolute difference in polity is how we capture homophily, or similarity in levels of democratization. Absolute difference takes larger values when two countries are further apart on their level of democratization. And so the lowest value that we can get, 0, indicates that two countries have the most similar level of democratization and therefore might be the most likely to form an alliance. C inc, again, is our defense capacity. The node covariate for C inc is telling us our alliance is more likely to be formed with nations that have more capacity for defense. And the absolute difference is the corollary. Are alliances more likely to be formed among pairs of nations that have similar levels of defensive capacity? We'll specify our estimation routine. One quirk about TERGM is we actually have to declare how we want to estimate it. The default and most common practice is CMLE, which stands for conditional maximum likelihood. But because TERGM can often get computationally intensive, we have more flexibility over how we might want to specify it. In most applications, CMLE is kind of the benchmark we go against. So we'll run this first TERGM. And as you can see, despite all my complaining about how computationally intense TERGM gets, it ran in a second. And that's because right now, it's just a logistic regression. So if we look at these results, what they're telling us is simply the logistic regression, bless you, results of tie changes. And so we have a baseline estimate of the conditional probability that a tie will change at random, which the negative 2.9866 is telling us it's extremely unlikely. We could feed that through a logistic link function if we wanted the exact probability, but it's going to be very small. The node cov polity is negative, and it's 0.04. And so what we can do is exponentiate this coefficient. And we get the odds ratio of a tie forming per unit increase in a nation's polity. So the odds ratio of 0.96 is telling us that each unit increase in the polity measure reduces the likelihood that alliance will form with that nation by about 4%. Or I should say the odds that a tie will form with that nation by 4%. We also get this absolute difference parameter. This is how we're capturing similarity. And so this measure is capturing how close the polity scores of two nations are. The negative coefficient is telling us that as the absolute difference between nations increases, as one nation gets more democratic and the other gets more authoritarian, the likelihood of an alliance between the two goes down. By inverse, as two nations get more similar, democracies and democracies, authoritarianisms and authoritarianism, alliances tend to form more frequently as well. Below it, we also have the node covariate for conditional for the defense capacity. And interestingly enough, we're actually not seeing an effect from this covariate at statistically significant levels. If you're fine with p-values, that you may be skeptical. And we also aren't seeing a coefficient or at significant levels from the absolute difference in national defense capacities either. And so what this is suggesting, at least from our very, very simple model, is that nations tend to be choosing alliances based on kind of governing philosophies, authoritization, and democratization, as opposed to necessarily strictly strategic interests, such as defense capacities. It's kind of interesting. So, we'll wait momentarily before we get into the marginal effects stuff, but we won't have to deal with that too much. Do we have questions about interpretation before we go back to the slides? Go ahead. Yeah, absolutely. So this is essentially the intercept in our model. And so what it's telling us is how many edges change between panels by random chance alone. And so if we were to take the logistic link function of this, it would tell us the probability by random chance that a new alliance will form conditional on everything else? Yeah, good question. Yeah, thank you. Do we have other questions about interpretation before we keep going? Cool. This is where we can start to get a little weird in terms of thinking about endogenous processes. So what we've talked about so far is how specific cases of ergom and tergom reduce to logistic regressions. And these are things that we can handle in a very kind of straightforward kind of way. But a lot of the complexity and where the assumptions of tergom really start to shine is when we start trying to account for endogenous change processes. So let's think about, can I do 2 blackboards? Maybe not. I don't think we have the space anyways. Okay. So let's think about a change process that looks something like this. We have a network at t equals 1 of 4 nodes, and we have a network at t equals 2 between 4 nodes. And what we've seen is we have 2 old ties dissolve and 1 new tie form. And so one way of thinking about tergom in the context of 2-panel data is that the network that we're actually modeling is the change network itself, meaning what is the network of new ties forming. And so in this way of thinking about it, our dependent variable is actually this network. It's the single tie that emerges between waves. And this is the network that we're modeling, because this is the only new formation we see. Now, the reason that's important is if we think about how endogenous characteristics are included in a tergom, we are essentially saying that the characteristic is endogenous to this change process. So another way of stating it is that tergom assumes that ties form in parallel. There's one moment in time where all these tie changes essentially emerge in unison. Another way of saying it is that when we're capturing an endogenous statistic, the probability of a focal tie forming is assumed to actually contain some information, or at least is treated as containing some information on the ties that will form after it, which is strange. So this is often a reason why tergom is critiqued. So we can think about this as both a strength and a limitation of tergom. Because on one hand, this assumption of one of discrete time processes, meaning that we're assuming that we're containing all the relevant information for tie change within a single moment of time or in the past network panel. And that's a very limiting assumption because we're not actually accounting for the order of those tie changes. It could be the case that I form a tie with somebody, I withdraw that tie from somebody, but before I could withdraw it, somebody else formed a tie. All that information on what the structure looked like when the network changed is lost in tergom, or at least dealt with by assumption. And that assumption is any measurement error we're getting is not correlated with what we're trying to estimate. That's a limiting assumption. But we also get an important utility. Because when we talk about Siena models tomorrow, actually I won't be here, when David and you guys talk about Siena models tomorrow, what you'll be talking about is how networks unfold as sequential changes occurring in a single moment of time. And what that means is some tie changes that are by definition occurring at the same time can't be captured by Siena. So if we're thinking about this in an alliance network, does a single nation enter into alliance by itself at once? Sometimes. But frequently there are coalitions between alliances. The UN formed because multiple nations were negotiating for some type of agreement to protect their national interests. By definition, those ties were negotiated and created in the same temporal moment. That's not something that's dealt with by Siena models. And so even though we get error on one side with a tergom, we also get utility because we can actually capture that endogeneity in an explicit way. So this is not to say that either model is better or worse. Different capabilities, and in some cases, different assumptions driving those capabilities. So this gives us the two differences, which are the distinction between how we're thinking about a network change process, and specifically the effect of endogenous statistics. What I'm calling here between panel dependence and within panel dependence. So between panel dependence is essentially saying, am I forming a tie because the network structure looked a certain way in the past? In other words, am I essentially forming a triad or closing a triad because it was opened at a prior time point? And so the idea here is that individuals or other types of actors are nested in some type of network and are updating their tie change decisions based on prior network structures. That's kind of like a Markovian way of saying it, but we actually don't need it to be a Markov process if we don't want it to. And in this case, one of the things that's really nice about TERGM, when you're only doing a between panel model, it's still a logistic regression. And the reason is because we're meeting a sequential exogeneity assumption. My tie now is independent of my tie in the past. Where we start getting estimation problems is in the second way of specifying endogeneity, and that is with within panel dependence. Within panel dependence is, again, referring to ties that form as parts of complete structures in the unobserved temporal moment between panels. In other words, we are talking about the ties that form as parts of complete structures endogenous to this change process. So in a hypothetical account, say we see a triad emerge between panels as we have on the graph right up on here. What that's saying is the tie more likely to form when it emerges as part of a complete triad between moments in time? So it's not simply that a single tie is forming in an unfolding sequential order. It's that ties are forming in unison as parts of complex substructures. Again, this can be a very powerful utility. If we're modeling coalition formation, that might be what it looks like. We had no group in the past. We have a group now. Why? Because we got together and we organized. But it might not be capturing what we're often interested in, which is the sequential ordering. I am forming a tie with you now. I am saying you're a friend with me today because you said I was your friend in the past. That's a between panel dependency. Okay? And so these two processes are often conflated. And part of the reason is because as the time duration increases between two network panels, it becomes harder and harder for TERGM to accurately account for the between panel dependence. And that's because more and more tie changes go unobserved. But as our tie durations get smaller and smaller and smaller, our between panel estimates get more accurate. So we'll switch back over to R to illustrate what each of these processes look like. So now we're picking up right where we left off. And what we're essentially saying is there are various number of ways where alliances between nations are created in the year 2000 or between 1990 and 2000 because of what the network might have looked like in the year 1990. And so one of the easiest, or one of the probably relevant ways that this might occur is because there might be a conflict between nations in the past. So two nations that are at war with each other are probably less likely to form alliances 10 years later, or within a 10-year period. So we can control for this network, which is the network of military conflict in 1990, by querying the 1990 value from the list of networks called WarNet in the data. And we'll create a new network called ConflictNet. If we peek at it, I think it's an adjacency matrix. Yeah, it is. We get a bunch of zeros and ones for the different nations that are at war with one another in the year 1990. Now what we're going to do is we're going to run this second TERGM, including a new parameter, which is between panel dependency, because it is representing what the conflict network looked like in the year 1990 and the effect it has had on alliance formation between 1990 and 2000. So we'll run this. And interestingly enough, or surprises me, I'll say, is we actually don't have an effect from two nations being at war with one another. And so this is suggesting that we don't actually have evidence that new alliances are going to form between 1990 and 2000, more or less likely, conditional on whether two nations were at war with one another in the past, 10 years. So the other way we can specify between panel dependencies is by including lagged versions of the structural characteristics of the network we're actually modeling. So on line 108, what we're actually going to include is a second matrix called LSP. And what LSP stands for is lagged shared partnerships. In other words, it's the number of nation mutual affiliates two nations have in the past. So this is our specification of between panel triadic closure. Are two nations more likely to enter into an alliance if they share a greater number of mutual affiliates or other nations that are allied with one another? So we'll include this similarly to how we included the conflict network, which we specified above as an edge covariate. And what we'll also do, just for illustrative purposes, is demonstrate how you can calculate between panel dependencies in your own work if they're not provided neatly like they are with the AllyNet data. So here, on line 113, what we're specifying is a lagged effect from degree centrality. And so this is the number of alliances a nation has entered into in the year 1990. We're calculating it by simply using the degree command from StatNet on the first network we're observing, the 1990 network. And we're including it as a vertex attribute called lagged degree. Now, the reason this is important, and I want to pause here to emphasize this, never do this with an endogenous statistic that is endogenous to the change period you're examining. If you include this, a degree centrality term, for the second panel wave, that's going to bias your ERGM estimates because we are no longer properly sequentially ordered. If we want to include that effect, we need to do it through the StatNet under the hood endogenous terms. We can do this only when we are properly lagging the temporal order. Okay? So we'll calculate this, and now what we have is actually a node covariate in our model called lag degree centrality. We can now run our TERGM 3, as it's elegantly called here, to capture the between panel dependency of not only military conflict, but past shared partnerships in the alliance network and the overall number of alliances a nation was involved in the year 1990. So we'll run this. And again, very fast. And so we get our log likelihood very quickly. We've preserved sequential exogeneity, which means this is still estimated as a logistic regression. So we can summarize the model. And now what we can see is that we do have some evidence of between panel dependencies down at the bottom here. What we first have is evidence of our lag shared partnership with a coefficient of 0.49, which is telling us, if we exponentiate, forgot what I was doing for a second there. And what we get is an odds ratio of 1.63. And so this is telling us for each shared partnership that two nations shared in the year 1990, the odds that a new alliance will form between those two nations increases by about 63%. So for each nation, each mutual affiliate or mutual ally in the alliance network in 1990 increases the probability or the odds that a new alliance will form by 63%. Go ahead.
Can you talk through best practices for talking about your coefficients, because you do both log odds, probability? Which makes the most sense to people? I found people have sort of told me to shy away from talking about it in log odds because it's harder for people to grasp that idea. But I'm just curious about best practices.
Oh, this is like a slam dunk. This is what I'm going to next, if we can pause this for a second, because I also happen to have written the paper on this, so in the ERGM. So don't worry, I'm about to push my own agenda, and I feel like I've got the right crowd for it, so this is great. So we're going to get to this just in a second with the marginal effects framework. But the second coefficient we have here is the lag degree. And so what this is telling us is that each unit increase in the number of alliances a nation held in the year 1990 is associated with a reduction in the probability that a new alliance will be formed between 1990 and 2000. And so what we're essentially seeing is a tendency for nations to rely on triadic closure or mutual affiliates in the past to inform new alliances. But they're also, strangely enough, avoiding the nations that had consolidated alliances in earlier periods. Okay, best practices. Go ahead, Jim.
Is the avoidance effect, I'm just trying to wrap my head around some of the substantive pieces here. So you interpret that substantively as saying it's because it's an addition model, and so there's no additional ties among people you've already connected to?
It could be the case. I think that's the analytic sociology way of saying it. My way of thinking about this is between 1990 and 2000, we had a major political realignment between Western nation powers and the dissolution of the Eastern Bloc and formation of African Union alliances. And so I think part of it is because all the prior ties in 1990, right after the Cold War, or the Berlin Wall fell and Soviet Union collapsed, A lot of it is kind of restructuring over here, and the prior alliances existed primarily in the West, which were essentially at the threshold you're talking about. That's my interpretation, but I'll be honest, I have not dug into it. Good question. Okay, so interpreting effects. So I will caution you by saying this is me pushing my own agenda. So not everybody agrees with me, but I think some people do. So what we've talked about so far is log odds and odds ratios. And one of the weaknesses of odds ratios is it's all on a multiplicative scale, right? So if we have a very low probability to start, we can have a massive odds ratio of like 100. And it's not actually that much of a change in the probability of a new tie because we have a low base rate. So one way of handling this is by estimating marginal effects. And so the ERG margins package I developed with the idea of trying to make marginal effects interpretations more plausible in TERGM and ERGM more generally. It also dealt with what's known, the second advantage of marginal effects is not just interpretation, but it deals with the problem of scaling or non-collapsibility. Have people encountered this before? Okay. What it refers to is any nonlinear probability model, including a logistic regression or a probit regression, ERGM is just one case, the variance of any unmeasured term or model specification gets absorbed into the coefficients. And so what that means is even though our Z statistics and our assessments of significance are not being affected, the size of our coefficients is either being inflated or deflated in proportion to whatever the variance of the omitted term is. And so when we want an effect size interpretation, we need to do something to account for that variance inflation or deflation. Marginal effects is one way. The other reason this is helpful is because the scaling and non-collapsibility problems can bias your interactions, and they can prevent you from comparing coefficients between models. Marginal effects are robust. And so if you're interested in looking at the change in the effect of a variable or the change in a coefficient between models, marginal effects can do it, coefficients can't. Average marginal effects as well, yeah. So either the marginal effects at mean or average marginal effects can do it. Or if you're looking at an interaction, marginal effects can do that as well. Oh, I need another whiteboard. Okay. So for those of you not familiar with... Oh, so that wall is a whiteboard? Duke. Okay. Okay. So the idea behind a marginal effect is we have some probability of a tie forming as a function of some input variable. And the issue we have with the coefficient is in a logistic family form model, this is a nonlinear function that plateaus at higher levels. And so with the marginal effect, what we're trying to do is figure out what is the slope at a particularly representative point. And so rather than summarizing the effect on a multiplicative scale, which is what the odds ratio is doing, what the marginal effect is doing is simply saying, what is the change in the probability of a tie forming at a given location in the distribution of variables? Now we can pick that location in a number of ways. One way is to hold the marginal effects at means, where we're simply calculating the average of all our covariates and then getting the marginal effect for the one we care about. Another way is to pick a representative value. We might not actually care about the marginal effect for everybody. We want to know the marginal effect among authoritarian or highly democratized nations. We can do that as well. Pick a particular point in the distribution, fix the values at where we want them to be, and then calculate the marginal effect. Sometimes the simplest and often the most preferred way is the average marginal effect. And what we do here is rather than say, why do we care about representative values, we could get the marginal effect at every observed value and just calculate the mean. And if we do that, we can say, what is the change in the probability of a tie given a change in a covariate, holding everything else at the values that are observed. Now, the main advantage of the average marginal effect is your statistical assessments of significance, or z-values, are actually always going to be the same as your coefficients. The disadvantage of the average marginal effect is when you're in big sample spaces, as you often are with TERGM, or high-dimensional models, it takes a really, really long time. Not really, really long always, but often. And the standard errors take longer. And so sometimes it's useful to simply hold things at representative values. So the ERG margins package implements both marginal effects at means and average marginal effects. And the only difference is after ERGM dot, do you write AME or do you write MEM? That's the difference. Everything else is the exact same. Not under the hood, but in terms of what you guys deal with. That's the exact same. And so what we're going to provide to the ERG margins package ERGM.MEM is the model we're working with, TERGM_3, and then the variable we want to interpret. Here, this is the lagged shared partnership term. And so the way we can interpret this, and apologies for those who can't see it, is the marginal effects at means is 0.005. And so what that's telling us is for each additional shared partnership two nations had in the year 1990, the probability of them forming a new alliance between 1990 and 2000 increases by about 6 percentage points, while holding everything else at means. So this is essentially practically the exact same interpretation as a coefficient, except we get it on the scale of probabilities as opposed to odds ratios or log odds. So we'll do the same thing for the lagged degree centrality, calculating ergm.mem. And here we get a negative marginal effect at means of negative 0.00001, which is telling us that each additional alliance that I had in the year 1990 is associated with about a 0.01 percentage point decrease in the odds that a new nation will form an alliance with me between panels. So the interpretation is the same as we had before, but now we are talking about the increase or the decrease in the probability rather than the odds. All good? I prefer it. Some people still interpret odds ratios, but the tide is shifting, and it depends on the field. So if you're in a field where people are anti-odds ratios, that's cool. Go marginal effects. If you're in a field where odds ratios is still acceptable, be an opinion leader, be an early adopter. Do it for me. Then you can still get away with odds ratios, but this is also an option, especially if you want to compare between models. Then you really need the marginal effect. Mm-hmm.
This might depend on like the context in question, but I really prefer average marginal effects. Is that also kind of preferred among people? This is just more of a curiosity.
I actually prefer the average marginal effect, but it takes a little longer. So here, it's not massive because our data isn't too large. But if you're working with like 20 network panels or longitudinal data of something like 1,500, 2,000 people, it doesn't actually take much because the size of the network increases exponentially as a function of each node we add. And so it actually has a pretty low threshold to start being annoying. And so it really depends, because some people, what they want to do is report essentially the marginal effect for every variable in the model, at which point even slightly longer runtimes become irritating. But if you're really just trying to pull out one relationship and say this is what the marginal effect is, it's not going to cost you too much usually. I will say one of the bigger bottlenecks is how many terms you have in the model. And so if you have something like 20, 30, 40 variables, which is not uncommon in TERGM, it can actually become really prohibitive to do it the average marginal effect as opposed to the marginal effect it means. But since you asked, this is the code for the average marginal effect right here. We're just changing the AME from the MEM. And as you can see, our interpretation for the lag degree centrality doesn't change much, but it isn't the exact same. So now, rather than a decrease of 0.0001, we get a decrease of 0.0003 per increase. So that's actually about twice the size. It's a relatively small starting value. So whether you make heads or tails of it, that's up to you. But there is a little bit of a difference there. And so the results aren't guaranteed to be the same. Substantively, they're usually pretty reasonable approximates. But there is a decision to make about what you think is the most representative quantity. Good questions. OK. So we've talked about between panel dependencies. And now we get to do the really more tricky thing, which is talk about the within panel dependency. And so what we're going to include here in TERGM 4, and this is the one I warned you guys, run it ahead of time because it takes a while, is we're going to include an endogenous statistic. So this geometrically weighted edgewise shared partnership term is a nonlinear term for triadic closure. What it's telling us is what is the effect of a closed triad per each additional triad with diminishing returns. So the idea here is that we're essentially penalizing additional mutual affiliates, so that if we have 3 or 4 additional mutual affiliates, the third and the fourth aren't contributing as much information as the first and the second to tie formation. We're picking, we can actually allow this to vary arbitrarily. Oftentimes that creates longer runtimes. So frequently what we do is pick a parameter and fix it there to speed things up, and then change that parameter around a little bit and see how robust our results are. Usually what we're trying to do is find a parameter that has good model fit and is relatively robust in terms of estimation. So when we include the GWESP term, what we're specifying is an endogenous triadic closure statistic. It's analogous to the lagged share partnerships we have up here, But the difference is, this is the between panels dependency. The lag shared partnerships is modeling the effect of us having a mutual affiliate in 1990. The GWESP term is modeling the probability that we form a triad all together between waves. And so these are the emergent triads. And when we run this model, the reason that we're getting really long run times is because the model no longer reduces to a logistic regression. Instead, what we have to estimate is the aggregate level model, which involves a very long sequence of Monte Carlo simulations that all have to be updated and can potentially get stuck in local peaks and get problems related to collinearity and all these things that make estimation more difficult. And so it's usually these endogenous terms, specifically the within-panel endogeneities, that cause estimation issues in TERGM. So if you followed along with me and you ran it ahead of time, what we can do is summarize the main results. And what we'll see here is we actually do get a positive and pretty powerful effect from the geometrically weighted edgewise shared partnership. But what's interesting is that effect actually isn't eliminating the effect of lag shared partnerships. There seems to be something going on here where we're both conditioning our alliances on the alliances that already existed and our mutual affiliates, as well as coalition formation. And so if we're thinking about how these alliances actually are forming, especially in the 1990-2000 window, it appears to be consistent that we are creating new alliances based on who we had alliances with in the past. But we're also getting together in groups and creating new alliances or creating new coalitions. And if that might sound surprising, I want to emphasize it's actually consistent with something we just saw earlier in the descriptive results, which is these new groups forming over here, which did not exist in 1990. And so any effect of all of these nations getting together and forming alliances with one another as part of coalition building would not be captured by the lag shared partnership term because those dependency structures did not exist in the prior panel. And so even though it's a little strange to think about, it is totally consistent with our data and specifically the unobserved change process that we're trying to capture. So in terms of interpretation, this, again, we can exponentiate. The interpretation of the geometrically edgewise shared partnership term is often a little weird because what it is essentially, I don't want to exponentiate this because it's going to make your eyes bulge. But what it's telling us is each additional increase in a shared affiliate between waves is associated with a new alliance forming, but there are diminishing returns to every single affiliate we create after that. In other words, if we share an alliance with one nation, that's going to bump up our probability of creating an alliance by a good amount. But if we share an alliance with two nations, well, the marginal gains from that second alliance actually aren't that helpful or as helpful as the first. And for every additional mutual alliance we have above that, it continues to decrease. So I'll get the marginal effect because I don't think it makes your eyes pop as much, but I don't remember. Yep. So here we actually have a quite small marginal effect. And so even though our coefficients are quite large, again, this is one of the reasons odds ratios can be misleading because it all depends on where things are at the mean and what the distribution of change statistics are. The effect at the margins for the average observation is actually not massive. It's smaller than the past dependencies we observed. And so this is telling us that we do have an increase in the probability of a tie forming for every additional triad closed between waves. But the marginal gains are actually quite small. It's something like a probability of 0.000007. Okay. So one other quick thing I'll do to plug my own research a little bit is when we get convergence issues, oftentimes what's driving the convergence issues is collinearity problems. And here we actually have a few telltale signs of collinearity. And where they're occurring is first, we have a massive coefficient here, which isn't necessarily wrong, but it's something to count of. But the bigger concern are these two. So this is the node covariate for national defense capabilities and the absolute difference. And their standard errors in their estimates have skyrocketed from prior models, where they already were reasonably large. And so what this is often telling us is there's not actually a lot of unique variation for them to work with, and there's a good chance they're collinear with the within-panel dependence GWESP term we just included. So we can evaluate this using the vif.ergm command, which also comes from ERG margins. And this will tell us exactly what the variance inflation factors are for every term. And what we're seeing is that the node covariates for military spending or defense capabilities and absolute differences are about 176, which is insanely large, especially if you're in a generalized linear framework where you're like, I don't want a VIF more than 4. 176 is a bit bigger. Now, ERGM is actually pretty tolerant of high correlations, but not necessarily this tolerant. And so when we're getting to this high of levels, one way we could potentially handle this, if we're trying to fit the within panel dependency, is to try to omit one of these terms, maybe the absolute difference or the node covariate, depending on which you think is less relevant on theoretical priors, and try to re-estimate the model, see if you can get a bit more traction. Okay. We have about 20 minutes left, so I want to go a little quickly here to show you some additional utilities we have of the TERGM specification. And so we might move a little briskly and skip a few slides. So the first thing I want to show you guys is how we can do model fitting. And so in the world of ERGM, the way we typically fit models is we simulate data from the model we actually have and see if the structural characteristics of those networks are consistent with the structural characteristics that we actually observe. Usually what we're using is the terminal network as the goodness of fit criterion, meaning that we are comparing our projections to the second network panel, but we can use other panels if we want to. So BT, ERGM, and StatNet both include a goodness of fit command, and they contradict one another. And so what we're going to do first is just detach the BT ERGM package and reload StatNet, so we make sure we have the right version of goodness of fit included. We'll run the GOF command, and as we see R is worrying, what it's currently doing is simulating a distribution of networks from the model that we fit. And what it's doing is on every single network, it's calculating the distribution of edgewise shared partnerships, the degree distribution, the distribution of ties connecting focal statistics, and comparing those to the data we actually have. So if we run line 190, this is the output from the very extensive procedure that we just got, where StatNet is reporting here how many edgewise shared partnerships we actually saw versus how many were contained in the simulations versus the data. And even further up, we get summary statistics for other things condensed here. This is just the edgewise shared partnerships, but it's a lot of output is the point. Most people don't report this table or spend too much time looking at it. What we usually do instead is plot it. And so we're going to use this plot.gof command, which inherits from ERGM. My R is a little outdated, so you might not have to do some of this par mf row thing here. But if you are having problems plotting it, just replicate the code up front. And what we're going to first do is just change the plotting margins so we can plot all the goodness of fit stuff we want to. And then we're going to use the plot.gof command from the ERGM package. And what it's going to give us is plots or figures summarizing the performance of our model with respect to the structural characteristics we observe. And so what we're seeing up here is the model statistics are reporting how many ties or the proportion of statistics simulated from the data that align with the number of ties connected to those statistics. In other words, what are the edge counts for every single statistic we observe? The black line is tracing our observed data. The blue dot is the mean of the simulated distribution. The black band is the median, and then we have our box and Wister plots. And so what we're seeing is for the distribution of statistics, it falls in the range, but it's not as centrally located as we might hope for. In terms of the geodesic distances, the path lengths between different nodes that we're seeing in the network, it's doing pretty reasonable. We're getting the general shape. Most of the observed data is actually falling between the box and whisker plots. We're capturing the right amount of disconnected components, which in this network is actually quite critical because we had all those isolates we were observing in the first two visualizations. Where our model sucks is in the degree terms and the edgewise shared partnerships. So here our degree distribution is not great. If that was the only thing that was wrong, it might not be fatal, but it's not good. And so this is definitely something that would raise eyebrows. Partly what the model's doing is overestimating the degree centralities of nations between 2 and 14. And it's underestimating a huge spike here where some nations have a ton of connections and are accounting for a lot of alliances. And so we're missing a lot of the nodes that are drawing a larger number of connections. The other place we're doing really, really bad is our simulated networks are dramatically underestimating edgewise shared partnerships. And specifically, we're missing this high level of clustering that we saw before with all of this coalition building. Now, if this were a research application, I'd be extremely frustrated because the first step you take in trying to fix these goodness of fit issues is to include a term that captures that statistic. So if I were to not see the model we just fit, and I looked at this plot, I'd be like, oh yeah, you've got to include a term for triadic closure. We already have 2 terms for triadic closure. This is bad. I would be upset about this in practice. The other thing that we could do that we haven't done yet is try to include additional terms to capture degree centrality. So there are additional parameters we could include, such as geometrically weighted degree terms that account for the distributional shape of degree centrality within the network. And we could include those as well with the hope that this fixes something over here. If I were in practice, just to give you some guidance on what I would be thinking about if I saw this, first, I might say it could be the collinearity problem we just encountered. Maybe we don't have an accurate estimate, and that's what needs to change. And so the first thing I would do is kick that out. I might also try removing the decay parameter, or the fixed term we had in the GWESP argument, in an effort to allow for a more flexible edgewise shared partnership distribution. The other thing that I'd be trying to think about is try to bring in additional knowledge or theoretical priors. So one of the things that we often get here is when we see a spike in the degree distribution, we might say that's because we didn't include a degree term. But what it can be the case is it can actually be selective preferences on other attributes, not just degree. And so it could be the case that there's some other exogenous characteristic of nations. What is their productive capacity? How much money do they have? What is their educational training that might drive migration or create other political interests that could actually be creating spikes in degree centrality at a specific location? And so what I want to emphasize here is even though the knee-jerk reaction when we see these things is to control for that term, degree or edgewise shared partnerships, it can actually be misspecification on other terms that create the lack of fit. And so that's always something worth exploring as well if we have the data and capacity to. Jim?
In this case, I think that's an illustration of what's how to do this degree 1,000%. In this particular case, isn't it partly just because this is actually a one-mode projection of a two-mode network? So I join NATO, I join these alliance structures. If I'm a member of, if I'm aligned with NATO, I'm aligned with everyone else in NATO. So effectively, under the hood, two-mode network, it's the cliques that's creating these spikes.
I think that's reasonable, yeah. I think for this alliance network, it could definitely be the case. And one of the things that's nice about TERGM is we can do it in the bipartite sense too. So if we have this data, which I don't in particular because I didn't create these data, but the underlying data generating it is there's actually a certain alliance event that we can model within TERGM as a bipartite network. And presumably that should help us deal with some of this. We're also, because TERGM is very flexible, we could include edge weights to try to account for that redundancy in the original bipartite network and offset some of the projected clustering that we almost always get. And that could be another way of trying to handle it too. Yeah, good point, Jim. Okay, so we have 10 minutes left now. And I want to talk about two more things. One is alternative estimators. So what we've talked about so far is, lost my train of thought. What we've talked about so far is how we can specify within panel endogeneity and how we can do so with Markov chain maximum likelihood estimation. We also talked about how many problems that can create. Now, one way of actually dealing with this is to not estimate the model with Markov chain maximum likelihood at all. So something that Schuyler Cranmer and Bruce Desmarais have shown is that in sufficiently large networks, you can actually do a bootstrap logistic regression to get TERGM estimates. And so this is the method that BT-ERGM includes. And so if we respecify our model in BT-ERGM, we can load BT-ERGM in. And BT-ERGM has slightly different requirements for how you provide data. So we're going to just include the lag degree statistic as a covariate at wave 1 as well. It's actually not going to be included in the model, but BT-ERGM wants it there. And we're going to include this. And next what we're going to do is actually do a bootstrap estimation of our TERGM. And so the BT-ERGM command, you'll note, something that's actually very restrictive about BT-ERGM is we're only allowed to model formation. And so we can only model the new ties. We can't deal with some of the more precise modeling capabilities we're going to talk about in a moment. But something that makes it more useful in terms of estimation is now what we're going to do is simply just bootstrap the data, estimate logistic regressions to everything, and then report those estimates. So what we're using is the BT-ERGM command. And rather than specifying the estimate as MCLE, we're going to specify R equals 500 to represent 500 resamples from the data. We're going to specify parallel as multi-core just to speed things up, and 3 processors. Now, as this runs, I want to urge a word of caution with BT-ERGM. The key term here is bootstrap pseudo-likelihood is a consistent estimator, but it is also a biased estimator. And what that means is that it only provides valid results when our data are sufficiently large and we have sufficiently long time periods. In this particular case, the results from our bootstrap estimation are not going to agree with our Markov chain estimation. And the reason is we have 2 time periods of 160 nodes. Bootstrap pseudo-likelihood is intended for more like 5 panels at the minimum, thousands of actors. And if that's the case, we can actually get consistent estimates in a reasonable amount of time with bootstrapping, where our Markov chain estimates probably break down. But the trade-off is we need to remember it's only contingent on the amount of information available. In small samples, these estimates usually aren't reliable. I'll put another plug here. ERG margins works with bootstrap ERGM. So we can do it that way. Do we have any clarifying questions while this finishes running? Yeah.
What would you consider like a smaller sample where, the unreliability of bootstrap is
This sample is going to be a problem. So even the data we're working with, I think usually I don't feel safe bootstrapping till I have over 1,000 nodes. And even then, if I have fewer than maybe 4 panels, I'm probably not going to want to consider it unless I absolutely have to. Yeah. Those are the benchmarks I use. I don't think there's actually an established precedent in the literature, but it passes my sniff test. OK. So in terms of the bootstrap ERGM, we get our point estimates. But since these aren't normally distributed statistics, go ahead. My preference is at least 1,000 nodes, and I prefer at least 4. Again, that's my criteria. That's not a standard in the literature, so I want to be clear. So as we can see, we get our bootstrap means, we get our point estimates. This is the average of the bootstrap distribution. This is the point estimate from logistic regression. Recall that what I said earlier, usually our pseudo-likelihood estimates of coefficients aren't off by that much. And so sometimes people interpret the estimate, sometimes it's the bootstrap mean. We don't get our critical values directly. Instead, what we get is our bootstrap credible or confidence interval, based on the bootstrap distribution, because we might not have normal statistics. And what I really want to emphasize here is the difference between our Markov chain estimates, or Markov chain Monte Carlo estimates, and our bootstrap estimates. So the edges parameter from our formation model with Markov chain maximum likelihood is about 3 times the size of our bootstrap estimates. Our polity parameter also about 1/3 of the size in our Markov chain Monte Carlo model as compared to our bootstrap estimates. Polity parameter also way off. Edge covariate for conflict is quite different. And in this case in particular, with our Markov chain Monte Carlo model, we had concluded that histories of conflict actually don't affect alliance formation. And in our bootstrap model, we would conclude histories of conflict increase the likelihood of alliance formation, right? So the implications of our estimator can actually be quite consequential. In this case, because our data is so limited, I would not trust the bootstrap estimates. Even though our Markov chain Monte Carlo model didn't fully converge, it was at least consistent with our earlier pseudo-likelihood maximum or dyad independence model, and that gives it more face value in my eyes, whereas our bootstrap results are very, very different. And so this, again, is to just emphasize bootstrapping can be an extremely useful tool, especially when computational resources are limited. You're working with big data. If it's digital trace data, some big data type thing, that's great. But the substantive implications can be quite impactful, especially when we're working in small sample spaces. Okay. All right. We're going to have to run through the last bit of this a little quickly. But there's 2 final capabilities of TERGM that I really want to emphasize to you. And what we've talked about so far is how we can think about TERGM as a limiting case or restrictive case on tie formation. But there's actually multiple ways a network changes. So I forgot my marker. So if we go back to what I wrote on the board in this minimal change network example, only one new tie forms between these two panels, but actually two old ties dissolve. And so what that means is we can actually think of a second change process where the ties represent the ties that are no longer there. And we can treat this second change process as a second dependent variable. Now, if we're thinking in this framework, this is what's called a TERGM. It was developed by Pavel Krivitsky and Mark Hancock, and it references a separable temporal exponential random graph model. And this is exactly why, in the TERGM command, we have to tell TERGM that it's a formation model if we want to treat the new ties as the dependent variable. But what we can also do is include a second model in the same equation, wrapped in the dis parameter. And what this dis argument is saying is model the effects of each of our covariate on a tie dissolving. So what we're going to do in this TERGM is actually model both processes at the same time. I've omitted the GWESP parameter so that we only have a logistic regression, not something more complicated. And we're going to run TERGM 3. And what you'll notice is, once again, it actually runs quite quickly because we are working in a sequential exogeneity state. So the first thing I want to draw attention to, even before we interpret results, is that the formation side of the equation actually provides the exact same coefficients that we saw before. So we're just adding on to it by adding a second model for the ties that dissolve. But now what we can also interpret is the asymmetric effects, or essentially what is making it more likely for a tie to dissolve, not just for a new tie to form. And here we start to see some interesting things. So for example, node covariate polity is telling us that more democratic nations form fewer new ties, but those ties are also more stable. Because node covariate polity, even though not significant, is telling us that, that alliances are less likely to collapse for more democratic nations as well. We can also start to see kind of effects on, or potentially asymmetric effects, such as the absolute difference in polity to similar levels of democratization create more ties, and the alternative side, which is do more different levels of democratization cause old ties to disappear. I'm trying to see if there's anything else interesting that pops out. Node covariate military spending. So for our defense capacities, we didn't see nations forming new ties with nations that had high defense capacities. But we do see nations essentially maintaining the ties they already have if their connection has high military spending capacities or high defense capacities. And so there's a premium on maintaining those strategic alliances that support, essentially, that can support you in terms of military conflict. We also sometimes just get weird stuff. So for example, we get the negative coefficient for tie formation. People with more, or nations with more alliances in the past are less likely to create new ties. Also, nations with more alliances in the past tend to hold on to those ties quite well. It's kind of interesting. If we want the marginal effect, we can again get it, and we can do this to essentially compare the asymmetric effects. So this is the marginal effect at means, telling us that for each additional alliance we have, each additional alliance we had in 1990, it decreases the probability of a new alliance forming by 0.01 percentage points. But each additional alliance that we have also, let me say this right, decreases the likelihood of an old alliance collapsing by 1 percentage point. Okay, I'm out of time, so I'm going to just do one last thing, I swear, and then you're done with me. And that's just to circle back to what I said at the beginning, which is that we can also model stability and change as separate processes. And so far what we've been working within is the classical case of TERGM as a formation model, and then adding dissolution onto it. But another way of thinking about this is that actually we have two types of ties going on here. One is the ties that are persistent across time, and the other is the ties that change. And so TERGM allows us to actually model the effects on tie stability and tie variability separately. So this cross-wrapping is essentially predicting the likelihood, or predicting the probability of observing a tie given that it exists at multiple panels. Whereas the second parameter here, the second argument, the change parameter, is modeling the probability that a tie changes. Now I want to be clear because this change parameter is a little weird. It's modeling the probability that a tie changes in either direction. It could be formation or dissolution. Okay? So we can fit this model again. And what we get, again, at the top, the cross-sectional is telling us what is the likelihood that a tie will exist at any point in time or persist across time. We're going to see it at multiple observations. And the bottom panel, what is the probability that a tie is going to change? It could be formation, it could be dissolution. And so a positive parameter on the change side is going to be saying a tie is more likely to change between waves. A negative parameter is saying that a tie is less likely to change between waves. And finally, because that interpretation is a little weird, I wanted to show you you can actually replace change with formation. And so this model that I'm running right now, TERGM 3C, is giving us effects on the cross-sectional distribution, was the probability of observing any tie, and effects on the probability of tie formation, what is the probability of creating a new tie. And those are the same types of coefficients we interpreted earlier. The only word of caution, we cannot include cross-sectional dependence, formation, and dissolution all at once. We get a perfect collinearity problem in the same way we get an age period cohort problem. So we got to kick one of them out of the model, but we can always choose two. I'll end with that. Thanks, y'all.
Last questions, Scott, before we, very quick.
Yeah, Tom.
Yeah, so lately I've been getting familiar with TERGM-based applications like simulations, and there you specify a distribution parameter. And I'm curious, right, like one of the most basic things you say, like this is the typical length relationship. As far as like actual terms here, how's that? I assume there's already an edge term in a dissolution part of the model, right? And then as far as these applications where you specify a typical duration, like how does that get implemented here?
Yeah, that's a really good question. So edge's term in a dissolution model is telling us the probability that a tie will dissolve by random chance.
Okay, that's just the
Exactly right. So essentially what we're doing is saying every tie that does collapse, treat it as a tie in itself, and that's the tie we're on. In terms of incorporating duration, I'll be explicit in saying I haven't worked a lot in this area. I know, however, that the longitudinal and exponential random graph models that Tom Snyder's have developed to try to account for continuous time processes and account for durations as well. I know Pavel Kravitsky has also developed models in TERGM that attempt to incorporate tie durations. But in terms of the actual explicitly modeling of it, it's not something that I've done, and most of the TERGMs I've worked with have been strictly in the discrete time space, and so they haven't dealt with this during.
Thank you, sir.
Thanks,